thanks for being here. It's always it's always more fun if there are people in the room to talk to them talking to the screen. So thanks first of all. So we're almost at the end. I have two more topics that I want to discuss with you. Johannes has then at the end it says wrap up, which means that I will just give a highlight of what we discussed, what things I think are important, and also what you can expect from the final exam. So that is for the last session. Today I want to. So I titled it Probabilistic Methods, which means that it has to do with probabilities. It means that it has to do that it is closely related to the Monte Carlo methods that we discussed earlier on. If I ever would write a novel, then the title would be The Improbable Journey of Detected Photons, because really, if most of our techniques throw in a lot of light, and only a fraction of that light is detected, which means that it is on average very unlikely for a photon to be sent into tissue, and then after everything that can happen, be detected by a detector and also contribute to so the perpetual question: at what scale do we describe light tissue interaction, or at which scale do we describe light scattering? So we are now squarely in the realm of bulk tissue. We discussed briefly the scattering by. We discussed not briefly in this class. We discussed extensively the scattering by different particles. It could be as small as a dipole or as big as a red blood cell. But now this relates to bulk. The propagation in bulk tissue. So a few questions for you, just to warm things up and to get some idea of what we're going to talk about. Do you remember what who remembers what the scattering efficiency is? So just not a formal definition, but just a colloquial definition. What was the scattering coefficient?
How much
efficiency?
How much power is scattered over the power that comes in of light.
Yeah, exactly. And in the case of the efficiency, it is actually expressed as a ratio. So it's really the ratio of the amount of power that is scattered over the power. Then the scattering cross-section and the scattering coefficient. So these, and you also know their units. They were related, of course, to that scattering efficiency.
Scattering cross-section is like the chance of scattering on the material.
Yeah, but that could also be the scattering efficiency. Yeah. So I mean, you're not wrong, but let's try to get it a little bit more precise.
It's defined as an area.
Yeah, so it's a scattering cross section. So the units are units of the area, so that could be square meters or square centimeters or whatever. So do you know how it is related to that efficiency?
It's like the efficiency multiplied by the actual cross section. G.
Yeah. So the scattering cross section, or the absorption cross section, or any cross section is the efficiency times the geometrical area. That is sometimes difficult to define. So it is not a very straightforward definition, but this is how it is. And what is then that will be then in units of area. So let's call that meters squared. Then for the scattering coefficient, so mu of s. You also know that one. Yeah, go ahead. Yeah.
It's I think the sum of all these scattering cross sections divided by the volume in which the cross sections are.
So that is so the formal definition is the total scattering cross section. So let's say write it like this: sigma, the sum of scattering cross section divided by the volume that we are evaluating. So it is another way of saying that it is the density of scattering cross section, density of total scattering cross section. So if we have particles that are all the same, and they all have the same scattering cross section, then simplify this a little bit. It's the sum of n times the same number. It's just n times scattering cross section. Denominator. The denominator stays the same. And n over v, so that's the number of particles in a volume, is the density. So then we have this only holds in the linear case. We are allowed to simply add all these cross sections. We've seen a slightly more complicated case when particles can be close together. Then this addition is not so straightforward. So this purely linear relation may not hold. Dependent scattering. Can you? It's not on there. But can you describe the process? Can you describe dependent scattering?
Right, to have an additional interference of the scattering. So you have this structure value which comes that makes the non-linear equation.
Yeah. So what basically happens is that you're absolutely right. So what happens is that this sigma the total scattering cross section. So it is not simply a sum of the individual cross sections anymore. It becomes the total scattering cross section. So let's write it like this: total is a function of volume fraction or a function of density. Then, so this denominator changes and changes here, and it will change here. But mu s still, in that case, is still the density of total scattering cross section. The only complication is that the total scattering cross section is not simply a linear extrapolation anymore of the individual cross sections, but it becomes a complicated function. What was the phase function? Really important function.
It's a probability density function that describes where the photons go to after scattering.
So it is it describes how the light is redistributed into different angles after scattering effect. So it can be and you have to, of course, picture that in 3 dimensions. So in polar coordinates, that means an angle theta, which was the photons coming in this direction. Then the angle theta is the angle with respect to the incoming direction, and then the angle phi is the rotation around the axis. And p of theta and phi, so the phase function p of theta and phi, describes how much light is distributed into, is scattered into different angles on average. But of course, that was a function that is not so easy. So we had a parameter that summarized more or less the workings of the phase function. That is the anisotropy G. So do you remember what that is?
The amount of photons
going in the other direction compared.
That's correct. Anything else? There's a couple of definitions. So this is more like what you said is more like the interpretation of the definition, but it is you're absolutely not wrong. So
It's the average of the cosine.
yeah, that would be the formal mathematical definition. So if this is the incoming direction of incoming light and the particle is here, this would be the scattering of theta. So the deviation from the incoming angle, and there is rotational symmetry around this axis. Then the average cosine, the average of the cosine of theta is this scattering isometry. What you're saying is right, because cosine of theta is basically the so if these were vectors and the length of the vector would indicate how much light is scattered, then the projection of this vector onto the incoming axis would be exactly cosine of theta. So that means that cosine of theta represents the amount of light there's vector ontbinden. You could project these vector onto different axes, and cosine theta would reflect the amount of light that retains the original direction. So that's a very good interpretation. Okay, I'm going to skip the last few questions because we'll get to it. So if you think of probability, so the phase function is a probability of or probability distribution of probability density function, be precise, of scattering into different angles. We can also make probability density functions of step size of photons. And with all these assumptions or all these methods, we can basically take two roads. We can either implement in Monte Carlo simulations. That is what we have seen before. So that would mean, based on these functions, generate many random paths, calculate all the probabilities of the and score the probabilities of these paths, add them all together to get an estimation of the signal. That's one path. Another option is to use these probability density functions to calculate an analytical expression. So we could calculate the probability, likelihood of a generic photon path. So a photon path, let's say, that contains a certain length and a certain number of scattering events, and then integrate over all the variables. So the number of scattering events, the lengths, etc., to get an estimate of the signal. So basically, this is letting the computer do the work, and that would be trying to do the work on paper for as far as you can get. So we've discussed this, and what I want to do today is basically try to explore how far we can get. Exploring is not really far, but still to get. So if you think of these probabilities, then so what we're talking about. So first the limitations. So no fields, no interferences, no nothing. So what we're really thinking of now is this interaction of photons and particles, like they are both particles. So a photon bounces off of a particle, gets in the direction, and then bounces forward. It may be absorbed, maybe not. With the photon path, basically, it's just a great game of pinball. So there are particles in the medium. The photon is launched, and it bounces from particle 1 to particle 2 to particle 3, etc., until it is detected. Escapes could also be absorbed. Each of these events, each of these steps, have certain probabilities associated with them. the trick is now to first find these probabilities, and then tie them all together to calculate the probability of, let's say, this photon path. So the questions that we need to ask ourselves is, so what is the probability, of the likelihood of a given photon path? So let's say this one. What is the distribution of path lengths between these collisions? So we have, like the drawing here, we have longer path lengths here, let's say this one, and shorter path lengths here. So what is the distribution of these path lengths? What is the probability of absorption along that path, etc., etc. So these questions need to be answered. But before we do that, before we go to that, I want to brush up a little bit the statistics. So probability density functions, commutative distribution function. You can see the list here. So these. So we're going to start with these probabilities. If we have a probability density function, PDF, P of x of a random variable x, let's say that x can fall within a given interval. In this case, x minus and x plus. If it would be scattering angle, it would be between 0 and 2 pi, for example. If it would be path length, it could be between 0 and infinity. So that is the limits that are imposed. Then p of x times dx is the likelihood. Actually, that is misstated. It's the probability of the random variable falling in an interval from x to x plus dx. So finding the value of x, but then in a small. Probability density function is normalized by definition on that domain. So if you would integrate p of x over the values it can take, so from x minus to x max, then the answer should be 1. That imposes a normalization constant. So one of the examples that is strange. There should be an equation here. One example would be the step size of photons between interactions. That could fall with in the range from 0 to infinity. That is the step size it could take. The PDF itself, so the value of the PDF itself has units per length. That is per length, and if you would multiply it with a dx, so a small value, then it would be a true probability, so a chance, really a dimensionless number between 0 and 1. If you integrate it over all possible values between 0 and infinity, then the answer would be. So that means that the probability that the step size is somewhere between 0 and infinity, that has to be 1. I do hope that the rest of my equations are in the slide. We could also calculate the commutative distribution function. So that is in green here. It would be the probability that this random variable x falls within the range from x minus, so the lower range of that the variable is allowed to take, up until to some value x. So formally, you would calculate that by taking the PDF, the probability density function, and then integrating that from the lower limit up until the value that you next. There are alternative notations for this commutative distribution function. I'm just showing you because in some of the book chapters that I will send you later on this notation. We can also have simultaneously two different random variables. So let's say we have two random variables x and y. They can take x can take values between the interval x minus to x max, and y can take values from y minus to y max. Then the joint probability, so that is the chance of finding the random variable x between x and in an interval x and x plus dx, and the random variable y falling between y and y plus dy simultaneously is called the joint probability. So this would be the chance, the likelihood, the probability of finding them together. We saw that, of course, when we talked about the probability of finding particle one at certain position, or the particle at another position. So you can of course scale this to many random variables. Also, this joint probability function should be normalized. So that means that if you take the function, you integrate it over both domains, the answer should be 1. And the example that the very specific example that we saw earlier on is then the phase function, because it is the joint probability density function of scattering into different angles, into angles theta and phi. And then, of course, in polar coordinates, that means that theta could fall between 0 and pi, phi could fall between 0 and 2 pi, so that would be the integration limits. But if you would take then a proper phase function and you would integrate it over these limits, then the answer should be 1. That's the normalization. The units PDF are then, because of the integration over two angles, or radians squared. That is the same as 1 unit of solid angle. So this is different. So radians squared per radians squared, or per solid angle. All right. Many times we have to deal with joint probability density function, but we're only interested in the PDF of one of the variables, so only of x, or only of y. So the way to do that is to integrate over the other variable. Basically, that means that you're adding all the possibilities of the other variable to end up with the wanted. So that means if we want, let's say, p of x here on the left hand side, we have to integrate over the variable y. If we want p of y, then we have to integrate over the variable x. We saw an example of that as well. So the Rayleigh phase function, the joint probability density function of scattering into angles theta and phi, that was given by this expression, 3 over 16 times phi and 1 minus cosine squared theta. As you can see, there is no phi dependence in this phase function, but nevertheless, it is a joint PDF. If we want to calculate p of theta only, that means that we would have to integrate over the variable phi. So it means integrating this over 0 to 2 pi of that expression d phi. Of course, there is no phi dependence in the expression, so integration is simple. That just yields a factor 2 pi, which you can cross out, and then the result is this. Same thing if you would want to calculate the probability density function of phi only, we would have to integrate over theta. That is a little bit more complicated, but quite well doable. So from 0 to pi of this expression, remember it's polar coordinates, so sine theta d theta. You can make the usual substitution for cosine theta as x, change the integration boundaries, and then represent this one. So a flat distribution. We can calculate, so usually for these PDFs, the function itself is not so much of interest, but its moments are, so the description of the function. So we can calculate, for example, the mean, or the expected value of that. So if we know the PDF, P of x, then we can calculate the mean by using this expression. So multiply each value by its probability, and then add it or integrate it given this function. There's a few rules for that. If you multiply, intuitively you already know this, I think. So if you would multiply x by a certain constant c, then the mean would also increase by that constant c. If you would have two independent random variables x1 and x2, then the mean of the sum would be the sum of the means. It's also not surprising, I think. Anyway, you can also calculate higher moments of this probability density function. So higher moments means that you raise x to some power e, an integer power e, and then perform the same integration. So you can. That means that the mean is the first moment. You can also calculate the second moment by filling in x squared, the third moment by filling in x to the third moment. So if you look at these moments, then for m is 0, for e is 0, so m 0, that would mean just integrating the probability density function. That has to be 1. That was the normalization. So for true PDF, 0 for the moment start is 1. The first moment is the expectation value, the mean. The slide above, and you can go on. You can go on like that. The second order or the third order moments are not the most convenient way of looking at these PDFs. Much more appropriate is, or more common is to look at the variance. So the variance of that variable is basically the mean squared deviation around the mean value. So we have a variable x, we have a mean, the first moment, m1. The squared distance from that mean is x minus m1 squared, and the average of that, or the expectation value of that, that's called variance. So you can do some manipulations with that. So we can, so within the square brackets, you can work out the product. So you use x squared, and then the cross term, and then 1 squared. Then the expectation values can be taken from each of these terms, like that. And then an equivalent expression, and that is the point here, an equivalent expression for the variance. So the variance is then the expected value of x squared minus the squared value of the expectation. So in this case, what would happen if I have let's say I have a random variable where the mean is 0. What is then the expression for the variance? I have a random variable that's this is 0, and the random variable just oscillates around 0. So what would be the variance? So given the last expression, what would be the variance of that?
The expectation value of x squared doesn't have to be 0, but the expectation value of x is, I think. So the variance would be the expectation value of x squared. No.
Expert.
on the
Second.
expert.
Yeah, so of these two terms, which one would be 0?
The second.
The second.
Yeah, the second one. Yeah, exactly. So the second one will be 0, this one will not be. So then in that case, the variance will, the second moment and the variance will be. That often happens because if you have some signals, some random signal that translates or whatever, usually there is a constant offset. So often there is a constant offset that you can simply subtract to bring it back to 0. In that case, you would have this. Rules. If you want to calculate the variance of a transformed variable, so if you have x, variable x with a given variance and you transform it linearly, the variance of the transformed variable is given with. If we have two independent variables, x and y, then the variance of the sum of these two will be the sum of the variances, only when they're independent. Let's look at an application. Suppose we have a complex random variable. So that could be an electric field or something that has been scattered and randomized. And also suppose that we have a joint probability density function for x and for y. So that is so suppose we know that. And now we want to know the distribution of not of x and y, so not of the real and imaginary components, but we want to know the distributions of the amplitudes and the phases. So the complex plane, you could describe it as x and y, but now we want to know the length of the vector a and the phase angle. So how to go about that? Do you know? Or
Sine and the cosine.
That's definitely knowledge that you need. So, so one click too late. So the question is how to transform that. So let's say we know P of x and y, how to transform that into a joint probability distribution of amplitude. The answer is so you can use the same expression, but you have to calculate scaling function that is the determinant of what is then called the Jacobian matrix. So that Jacobian matrix relates the change in x to the change in a, change in x to the change in phi, etc. So we need to calculate this determinant to make that scaling equation. So a question for you now. So for like you said, for this complex number, x is a times cosine phi and y is a times sine phi. Can you calculate that determinant? Yeah, that's exactly true. So that means, so J the determinant of Jacobian matrix is A. And that means that we can express P of A and phi as A times P of x and y. Okay, so let's give this some more meaning. So let this joint probability density function of P of x be a normal distribution. So we have P of x and y is as you can see. And now we want to know the amplitudes, the distribution of amplitudes A and phase. We also know, of course, that A is x squared plus y squared square root. That phi is the arctangent of y over x. Can you now derive with knowing that this Jacobian was the determinant of this Jacobian matrix was A. And now give an expression for P of A. The joint probability density function of amplitude and phase.
Just A times the S.
Yeah, it's just A times that. That is true. That is. But then now, in terms of A, I mean, if you want the probability density function of A, you don't want to have x and y.
You can just write it as A squared. So
yeah,
that's A squared, right?
Yeah, so it wasn't meant to be a difficult question. I just want you to look at it. So. Yeah, so the factor A comes from the Jacobian. Determinant of Jacobian, A squared here is then x squared plus y squared. So, this happens to be, and I did not bring one. That is silly of me. If you take a laser pointer and if you shine it on a granular wall or something, then you see this this pattern of dark and light spots. That's called a speckle. If you would measure the intensity of these of this pattern, of the speckle pattern, spatial distribution of it, you would calculate the distribution of the intensity values, or if you would calculate the intensity of the electric field values, it would follow this distribution. So this has some physical. Okay. Let's continue with that. So now this is still a joint distribution of amplitude and phase. So let's say we're only interested in amplitude. What would be the marginal distribution for amplitude? What we need to do?
The integral over phi.
Yeah, the integral. Yeah, that runs from.
And since it doesn't depend on phi. It's just the sum of the boundaries.
Yeah, that is in this case is from 0 to 2 pi. So that would just add a factor of 2 pi, which we can cross out here. So this would then be the distribution of amplitudes only. This is called a Rayleigh distribution. Amplitude, electric field amplitude, we cannot measure. We can only measure density. So, now I'm interested in the probability density function for the intensity. So I project this laser pointer on the wall, and I want to know what distribution of intensities is. What I would have to do is to calculate the square of this amplitude. So first question is, now we know the probability distribution function of the amplitude. We want to know it of So we need another coordinate transformation. So what we need to calculate the determinant of the Jacobian matrix for that. So what is the Jacobian that we need to calculate now?
It's just a matrix one.
Yeah, so it is not a matrix because it is only one variable to another. So that is, it makes life a little simpler. So it is not.
Just two ways.
We have the denominator and the numerator switched, so it's 1/2. So we need to calculate dA, dI. So the easiest way to do that is first calculate dI, dA, that is 2a. That means that 1/2. So it's 1. So if we do that, and we fill that in, so then we get these steps. So this is the left-hand side is the original PDF of A, then multiplied with the Jacobian. Let's keep calling it the determinant of the Jacobian matrix. In this case, it is just a number 1/2A. And if we then, it means that A is cancelled. The factor 2 appears here. Is the process clear?
The only step for me is not clear where the Jacobian comes from.
So Jacobian is again.
Yeah, so it's needed to go from one coordinate system to another.
Yeah.
But
Yeah. So basically, if you have two coordinates, it really looks like a matrix. So on the left hand side you have the coordinates that you want. On the right hand side you have the coordinates that you have. And the derivatives here are basically from what you have to with respect to what you want. So in the case of that we're considering now, we want to know intensity, we know amplitude. So what we would have to calculate is the derivative from amplitude with respect to intensity. We of course have an expression that relates it the other way around. So what we can do first is we can calculate DI. So this is what we need to know, the RDI, because we know amplitude, we want to know intensity. So this is what we need to calculate. We can calculate the other way around, the IDA, that is the way, and then the RDI is adds trickery. Then okay, now the real question, the question before the break. So now we have this we have derived actually this intensity distribution of the distribution of intensity in this speckled field. Shiny laser point. Can you now calculate the average intensity? So the first moment. So knowing this, and I guarantee you that this expression is normalized. And now calculate the first moment. But we need to do it together.
I'll just say 0. 4 minus infinity. This one. Thank you. This one. This one. So just
Mhm. Nee.
Dus wat is
Ja.
Dat dacht ik. En dan kom je mee. Dat is cool. Ja.
Nee, ik had maar 1 keer nodig. Want als je. Ja, nee, dit. Maar dan ligt het een beetje aan wat je grenzen zijn. Maar ja, als je 0 tot I max hebt. Dan sta je daar. Maar I max. Maar dan als I max nou groot is, dan heb je wel het exponent. Maar ik had hier ook inderdaad U als I genomen.
Maar wat is je V?
Mijn V is geïntegreerd van dv, dus ik had die exponent. Di, dat was mijn dv, en dat integreren geeft v is min 2. Keer die exponent.
De afleiding van het land van ik min 2
Yeah, I'm not really sure.
So it's just 0, right? No. Oh.
No.
From minus infinity to infinity, though, right?
Yeah. It's not. Don't be fooled by the. It's not an easy. It's not an easy question. So let's just do the first steps. So, what is it exactly that we need to calculate? We want to know the first moment, the average intensity. So, and we know P of I. So, what do we need to calculate?
Sin theta I divided by the P of I di.
I would choose 0 because I don't think intensities.
No,
Yeah,
intensity is like a power. There is no negative values. Yeah, from 0, but it can be infinite. So this is done the first time. Is 0 to infinity of I divided by 2 times squared. Exponential minus I squared di. What would be a logical next step to do?
I have used partial integration.
Yeah, yes. Okay, so but first to make life a little bit easier, let's make a substitution. So let's say x. I over sigma squared. And then it becomes a little bit more palatable. So it still we would have now integral of x times exponential minus x. D. So what would di become in that case? Make the substitution.
2 sigma squared dx.
So I can make the 2 sigma squared here. Dx. The integration still runs from 0 to infinity because that is only if you multiply infinity with a constant, it does not matter. And if you multiply 0 with a constant, it also does not matter. So this still runs from 0 to infinity. So the question now is solve this. I heard someone say partial integration. That is exactly correct. Have you done it or have you solved it? Do you care to write it? Would you care to write it down? I know you hate this. You guys hate this. But
I do make it,
I'm
it's okay.
I'm lazy, so. If you the board is yours.
I don't know how you guys do it. All this part. Yeah, so here's a minus, so I think that we come to plus. Okay. For infinity, this becomes 0. And then for 0, this also becomes 0. Infinity. Infinity, this becomes 0 again, but for 0 it doesn't. So it becomes 1. Then we have to substitute that. No, I don't think so. I guess this should be my answer then. Is that correct?
Not entirely.
No, because I have something else on paper.
Oh.
Because I didn't use this substitution.
Anyone has an alternative?
I had somewhere for sigma squared. So I also used the other part. Sorry,
Do you know it? Remember?
So this part we pick. I've written it down slightly different terms. Let's see what we did here. So the integral can be expressed as an integral from a to b. of f function f times g prime. So this is where the partial integration comes in. Let's integrate that on dx. Is given by f times g. So here is g prime, f times g from b a to b minus. And we need to go from a to b of f prime g. I think that is not different from what you.
I think that's the same.
I think that's the same.
Yeah, so that is. So the smart choice is now here to pick f as the function x, g prime as the function exponential. So if f is x, then f prime of course is 1. If g prime is exponential minus x, then g is minus exponential minus x. Great. So then, we can just show it. And here we have this term is x times minus e to the power x from infinity to 0. This term is the integral of now only g, because f prime is 1. So only g from minus infinity to infinity. So that would be my pluses and minuses are correct. I think so.
So far we have the same.
Yeah. Okay. Then this is taking out minus exponential minus x by integration. And then, so for infinity, this will be 0. So minus 0. So x is 0, so this is 1. For 0, this one exponential is 1, this is minus 1. So minus 1. It's 1. Okay, great. So then, we calculated this integral. This prefactor was there. So the result of the whole integration. The result of the whole integration is then 2 sigma squared, so 2 times the variance. We can plug that back into this. So this is mean intensity. So we can plug that back into the expression of the intensity because we have 2 sigma squared expression here with 2 sigma squared expression there. The final result is the equation here in green. So the distribution of the intensity in this speckle pattern follows this exponential distribution. It's parameterized only by the mean value. Okay, that is the manipulations that we need to do. So let's have a break now. 10 minutes or so, is that okay, or do you want longer? Okay, then we'll start in 10 minutes. Yeah, ready to go? Okay, so this was all a little bit of introductory work, preliminary work, although we did solve a speckle pattern, which is important in fixing Johannes will, I'm sure, refer to speckle in this class on Friday as well. So now you know it. But back to this question. So the question of tracing photons as they go through travel through a medium. More or less showed this slide, and I've also more or less made this statement that we are really now again considering photons and particles as interacting. Let's say like a pinball game. So there is no interferences, etc. There's no phases. There is no fields. The application that I want to tie this to is called single fiber reflectance spectroscopy. That is a technique that we use in our group. Technically, it is exceptionally simple, I would say. So we have a broadband light source. That could be a halogen lamp, laser that emits multiple wavelengths, something like that. That light is coupled into a fiber that is sent to the red part. That's a coupler. I'll get back to that later. And is coupled into a measurement fiber, which is in touch with the tissue. So light is emitted from the fiber, but it is collected by that same fiber. Collected light is then sent back through that measurement fiber to the red part, the splitter part, and then sent to a spectrometer where it is analyzed in terms of wavelength. So it's an extremely simple setup. The only challenge is to make that coupling. So we have one fiber from the source and one fiber to the spectrometer. We somehow have to merge that into one fiber that goes to the tissue. So that is a technical challenge. But other than that, the setup is pretty straightforward. So what can we measure? Well, so the wavelength range of that light source is pretty broad. So let's say from 800 to 900 nanometers. Typically, in tissue, there is a lot of interesting absorbers in that range. So we have hemoglobin and oxyhemoglobin. These are the red and the blue curves, of course. Proteins in blood. There's water, of course, that is not even in this graph. But also compounds like beta carotene, bilirubin, there's more there, melanin, another form of melanin, that all contribute to the absorption of tissue. And as usual, the assumption is that if there is any deviation or any abnormality in the concentration or the balance between these absorbers, then something may be wrong. So if we can measure this balance, if we can measure this, these concentrations, then maybe we can predict if there is disease of it. So one question for you. So this is all absorbers. Tissue also scatters. It also influences the signal. So how does scattering behave versus wavelength? Roughly.
With the power of 4.
For very small particles, that's true. That would be Rayleigh scattering. That is inversely with. Yeah, that's absolutely true. If the particles are a little bit larger, then the inverse power scaling with wavelength is still true. Only the power is a little bit less. So it could be the power of 2. 1.6 or whatever. That is not well defined. But for small particles, you're absolutely right. For the somewhat larger particles, like cells maybe or etc., then it can be much. Roughly, that's the important. Roughly, it will decrease with wavelength. this is a logarithmic scale, so you will see a kind of straight line going. We have used this technique clinically as well to measure the occurrence of Barrett's esophagus. I'm not sure if you're familiar with that. That's hopefully, I would say hopefully not. So I'll briefly explain what it is. It is associated with reflux, so stomach acid that comes up. I'm sure you've had that sometimes. Some people have it chronically. If that occurs, then so the lining of the stomach wall is of course meant to handle that stomach acid. So it can, the wall of the esophagus of the slugdarm is not equipped to handle that. So if you have a lot of reflux, so there's a lot of acid exposure to that type of cells, then if it's chronic, then they cannot handle that. And it results statistically in a 50 times increased chance to develop cancer in that region, simply because of the exposure. So what happens in time is basically distinguishable in a few steps. So first of all, it would start with what is then called non-dysplastic. So non-dysplastic means dysplastic is a medical term for abnormal tissue. So non-dysplastic means that there is still normal. Basically, it still looks normal, more or less looks normal. But there is this reflux, so there is this increased chance of developing cancer. If that continues, then the first step would be low-grade dysplasia. So dysplasia, dysplastic means abnormal tissue. So dysplasia means abnormal tissue. Low-grade means that it is not very aggressive. So in cancerous cells, we distinguish between two types. We have our two categories. So we have stage and grade. Stage means basically how advanced the cancer is. So, think like, has it grown, or has it protruded some boundaries, or has there been some seeding, these kind of things. And aggressive is basically how fast it grows. There are types of cancer that are there, but that are dormant. And so the first step here would be low grade, so not aggressive, but yes, there are some changes. The third stage would be high grade dysplasia, so that means that the cancer becomes more aggressive, and then the final stage, and of course that is what we really want to prevent is really cancer of the esophagus. So true form of cancer. So the goal is, of course, the quest is, of course, to capture. So this pathway is well established. That has been from clinical studies, from histology, we know that. So if we can catch it early in this cascade, the early we can capture it, the early we can start treatment, and the early we can try to avoid it. So the really ambitious goal would be to capture it already here. In this case, where there is really there's really not that much going on in terms of cells going wrong or pathology going wrong, but we know that because the patient has this reflux, so we know that there is a high risk. So we could use it as a screening tool. So for patients that come to the physician with this complaint that, well, I have this reflux and it has been occurring for a time, can we now make a measurement, devise a measurement that is capable of seeing if already you're in one of these two stages. That would work something like this. And we would take a endoscope. So the instrument looks. I'm not sure if you can read labels. Would look like this. So this is the part that goes via the mouth to the esophagus. And then here we have a few ports, instrument ports where you can put the camera so you can visualize it. You see the visualization over there. There was also a port where you can put in an instrument. So that could be a tool to take away a little bit of tissue to look under the microscope, but it could also mean that we can put in a fiber to measurement. Water controls. So what Anouk did, Anouk is was one of our PhD students. She now works at the Antonie van Leeuwenhoek. What she did is take this single fiber measurement, place it on the tissue, take spectra, and then try to see if there's something abnormal in these spectra, something not what you would expect. So a typical measurement would look like in the figure there. So on the left hand you see 5 measurements. So the colors indicate the different measurements, and they are taken with 2 different fibers. Right? The difference is the diameter of the fiber. So one is a little bit thicker than the other. The thicker one is the one on top. Because it is a little bit thicker, it can collect more light. So if it can collect more light, then the signal will be a little bit higher. So that's you see it there. And the other one is this one. Then she tried to fit a mathematical model to that relates the spectrum that was measured to the concentrations, to the concentrations and to the scattering of the tissue. And that is what you see in the right hand here. So the red, in red is the, let's say, the average measurement of these 5 fibers. And then in black, dotted black is the fit, the theoretical fit to these measurements. As you can see, it is far from perfect. If you look, if you think back to these absorption coefficients. So now let's look at the absorption coefficients of blood, for example. You see that for oxygenated hemoglobin, it has 2 peaks around 550 to 600 millimeters. For deoxygenated, it also has peak, but not these 2 peaks. So if you then go back to the spectrum that was measured, then you can see that in these so there's peaks in absorption, that means dips in reflection, and you can see that they were present. So we do pick up some signal of blood, but with the quantification, because of the basically bad fit, the quantification is not so good. So the approach was here to try to use this get this data and then fit a model, that a physical model that we had, to try to extract these concentrations, and then from that get the tissue parameters. The inputs of that model would be the known spectra, so of hemoglobin, oxyhemoglobin, bilirubin. You saw them all. And some assumptions. So, for example, that scattering decreases, like a power also lambda to the power minus b with wavelength. That could be -4 for small particles, or something else for other particles. So there's some assumptions going in there, but the net result is that this model is hugely complicated. So this table, the point is not to discuss all of them. This table shows all the parameters that go into the model. So A and B for scattering, P1 to P3 also for scattering. We'll get to that later. And then here is the concentrations of blood volume fraction, oxygen saturation, then a number of parameters as well that describe all the other problems. So the model is hugely complicated. On the other hand, if we looked at the results, realize that the graph is a little bit small. They were encouraging. This is a so-called ROC graph. Have you ever seen one of these before? It has a sensitivity on the vertical axis and 1 minus specificity on the on the horizontal axis. Do you know what sensitivity is? Sensitivity of the test is.
Positive.
Okay. So there's basically the number of. So if you know that the patient has the disease, how good is the test in specificity? So what is then the specificity? So that was sensitivity. What is then the specificity? Yeah. So if the ratio that the test really turns a negative result if the person is not. So for an ideal test, you would want to have both of these high. So that would mean it would always give a positive. A high sensitivity would mean that it will always give a positive test if the patient is sick, and a high specificity would give a positive negative test when the patient is healthy. So it's a little bit complicated. This is then 1 minus specificity. So that means that the closer the line of such a test is to this axis, the better the test is. And that has, so this is a concept that comes from engineering. That's funny by itself. That means that if you plot it this way, that the area under this curve, the higher this area, means that the better, basically, on average, the test is. So it would be perfect if it would be perfect if it would be glued to this and this axis, then the area would be let's say 1. If it's a little bit imperfect like this one, then but it's still close to the axis, then the area. If you would have an area of half, so like this, then that would signify that the test is just as good as tossing it. So that is the whole point of this. I digress a little bit. Even though what we were not satisfied with is that the model was so hugely complicated, what we were satisfied with is that apparently 0.94 is not that bad. So it has potential. So our question is, can we improve it? Can we do better? So one of the issues that happened to occur is basically has to do with the manipulations in the surgery itself. So if we bring this fiber into the esophagus of the patient, we have to place it in contact with the esophageal wall. The patient, of course, breathes. So it is sometimes hard to keep it in place. So we've tested the effect of that. So this is a result from another PhD student who just varied the pressure of the fiber onto the tissue and tried to see what the changes in the signal were, in reflectance. So in the legend, you see the different pressures, graphs that you can see here. What he indicated here is blood absorption change, reflection change, and water absorption change. That is not true. It is the same tissue. What it gives is the apparent change in blood absorption, the apparent change in reflectance, and the apparent change in water absorption. So that is one point that we need to take into account somehow. We haven't found out how yet. So what he then did is evaluated the mathematical model that was used. And then this is the result. This is the summary of that. They don't like it if I show the slide, but this is the summary. It has 18 parameters. 18 So you get two spectra like that, and then there is a model with 18 parameters that is fitted to that. So we optimize these 18 parameters, and then we get an answer. So there's 8 parameters necessary to model the scattering coefficient and the phase function. There is 6 parameters for blood absorption. So we have the hemoglobin concentration, the oxygen saturation. There's also, if you remember maybe from the very first class, that if the red blood cells were confined in vessels, then we had a different response than when they were homogeneously distributed. So we have to take that into account as well. So there is water. The absorption of water is temperature dependent. So there is a parameter that accounts for that as well. And there is in most tissues there is some finite fat components which has an absorption coefficient which you need to take into account. And then there's 3 forms of melanin that also need to be taken into account for different skin types. So that is an additional 3. So we have 18 parameters, and that at some point we asked ourselves, yeah, okay, so we are doing this whole physical modeling, trying to do it as best as possible. But at some point, maybe a 20th order polynomial would also, and then maybe the polynomial coefficients would give you some information. So describing this model, and it's just part he particularly does not like. Describing this model took 8 pages in his thesis. So at some point, we thought, okay, we have to go back to the drawing board. This is a model that has grown out of hand. It has become too.
Did he make the model himself, or did he?
No, it is
learn from someone?
no, that is an evaluation, evolution of 20 years, I think. So this technique was first started in Roc Graph, and then they had a very simple, elegant model that did not work. And then they started adding and tweaking and these kind of things, and then at a certain point, in Roc Graph, the focus shifted. So the people that worked on it came to Amsterdam in our group, and they just brought model. And first we were unfamiliar with it, so we just let them go for a few years. And then when Anouk and Shu started, then we thought, okay, now is the time to start over, try differently. Try differently is what I want to do. We'll show you today. I'll talk you through it. The point is, the technique is really simple. It is only lamp to a fiber, one fiber into an endoscope, another fiber to a spectrometer, which you can also buy. That's really simple. The model that is the complicated. So there's a lot. So the physics side is not understood yet. That's good. And these are the questions that we had before. Okay. This is how the geometry would look like. So on the left-hand side, you have 2 fibers, one that injects light into the tissue, the other one that picks it up. What we are trying to model here now today is the situation in figure B, where there is only one fiber that injects light and also collects light. The trajectories that are shown there are paths of individual photons. So the dots represent scattering events, and the lines represent propagations. As you can see, there is a lot of light that travels fairly straightforward from one fiber to the other in figure A. There is a few photon paths that take much longer. And here in the single fiber geometry, even though the fibers is a lot thicker than the individual fibers there is a tendency, be careful, a tendency of light to be injected, traveling in depth, then being scattered back, and then traveling back to the fiber. So the measurement volume in this case is a little bit better defined than in that case. The path lengths are in general a little bit shorter. And also, and that's an assumption that I'm going to make the following year, is that that most of the signal is consists of trajectories that have scattering events, a few scattering events in the forward direction, then one scattering event in the backward direction, and then a few in the forward direction again back to the file. So one of the assumptions that I will make is that there's only one back scattering event. Of course, this trajectory immediately tells you that it is not true, so that it is an assumption. Let's see how far we get. With it. These slides were already, I just realized, in the Monte Carlo presentation, but I'm gonna go through them anyway, just to be thinking of the likelihood of a signal. So we know that if we look at transmission from a cuvette, we can apply Lambert-Pierce law, that is given an equation. And let's say that it evaluates to 1 out of 100. That would mean that one out of 100 photons, if you think of the interaction, as particles, scattered particles and absorbers interacting, that 1 out of 100 photons is transmitted. In this case, that means that 99 out of 100 photons are absorbed. So if the probability of 1 out of 100 photons being transmitted, if you can calculate the probability, so let's say the result is that 1 out of 100 photons is transmitted. If you can calculate the probability, that also directly tells us something about the, let's say, the probability of that signal, or an estimation of that, the likelihood of the signal, the estimation of the signal. So the recipe that was also in the Monte Carlo slides was to take the event. So let's say a photon traveling from A to B with a number of scattering events, break it up in sub-events, calculate the probabilities, the likelihoods of these sub-events, and multiply these to obtain the probability of the event. That only works when they are uncorrelated. And if there are more than one way, if there is more than one way to get to the event, so a photon going from A to B can have this path or this path, an additional way of getting the event, then we can add these probabilities. That is the so if we look at, for example, this geometry where we have a fiber that launches light into the tissue and one that detects light from the tissue, so A and B, they are separated with a certain distance. Then this what is drawn here would be a possible path for photons to get from A to B. So it would propagate to 1, it would scatter there, then propagate to particle 2, it would scatter there, etc., etc., etc. The probability of this specific path, this particular path, is then the product of the independent probabilities that make up this chain. So we have to. So if we just follow the photon, basically, we have a probability of traveling a length L1 to the first particle. Then there is the probability of scattering at R1. Then there is the probability of scattering when that scattering occurs. Then there is the probability of scattering from the direction corresponding to L1 into the direction that would bring it to L2. And after that, and then it repeats, because then there is the probability of being scattered to location 2. There again, probability of being scattered. There again, probability of being scattered from direction 2 to direction 3, etc., etc., etc. So basically, we can boil down this whole path into three steps that we need to calculate, and that we can repeat we can keep repeating. So step length, so the probability of scattering between traveling between steps, the probability of scattering itself, and the probability of scattering from one direction to the other. They will all be treated, of course, as random variables, so they will have an associated probability density function, which we extensively discussed before the break. So, yeah, so it's a slide from the previous presentation. So, so the approach now here is: can we find analytical expressions for these functions and then try to solve such a problem, or do we go to Monte Carlo solutions? So Monte Carlo we did. So now, of course, the question is: can we solve? Okay. Let's take a look back to the cuvette. So no scattering, just absorption. There's light coming in from here, intensity I0, light coming out. On the other side, intensity I. And PA is the probability of absorption per unit length along the path of the photon. Because there is no absorption, no scattering. In this case, the photon path will be straight. But in a scattered medium, that could also be a curved path, so just along the trajectory that the photon takes. Then, if PA is the probability of absorption per unit length, then PA times DL, PA of L times DL, is the probability of absorption between L and L plus D. That was the definition. That was the definition of the PDF. You could also interpret that as that PA of L is the probability density function of a free path length, so the length that the photon will take before it is absorbed. So, just different ways of looking at it. It's normalized, of course, because it is a true PDF. So, if you integrate it over 0 to infinity, let's show why it is not an integer. 0 to infinity, then the result should be 1. Okay, now let's assume that P of L is a PA of L is a constant, so there is no L dependence. Instead, the absorption probability is equal along the trajectory. That is probably always true for a cuvette. For a in tissue, it may not be true because you can have different layers with different components. If PA times DL is the probability of absorption in an interval of DL, what is then 1 minus? Yeah, the probability of not absorbing. That is in this case because there was no other mechanism. That means that that is scattering, transmission. Yeah. So the probability of not absorbing. So now if we now take two of these small segments, so, placed together, what is then this expression? So 1 minus A times DL times 1 minus.
Same for double length.
Yeah. Yeah, so it is then yeah. So if 1 minus PADL is the probability of transmission through segment DL, then this would be the probability of transmission through two of these segments, assuming that these probabilities are totally independent. So this would be the probability of not absorbing or transmission. Yeah, that is the caveat. So you assume that it is. So you can now look at any length, any photon path length, and break it up in segments size DL. And for each of these segments, you can do the analysis. So let's say we can break it up in n segments, capital N segments. And the probability of transmission, or the probability of not absorbing, between 0 and a certain length n, a certain length L is NDL, is simply multiplying out all these probabilities. Now let's do some manipulation with that. So we can take the natural logarithm of both sides. So ln p on the left hand side and the ln on the right hand side puts the n in front of the natural logarithm. If the absorption probability is not that high, so much smaller than 1, and then we can approximate the ln term. So ln 1 minus x is almost is approximated by minus x. So we can make that approximation. And then exponentiate back. So take the exponent of both sides. So here we have p again. And here now there's p exponent of minus p times n times dl. N times dl is the complete path length, so we can substitute that back in here as well. So p times l. Too fast. And basically, this is just Lambert-Pierce law. So we have now probability of a signal probability or a transmission probability of exponentials minus PA times L. And if you compare that to Lambert-Pierce law from earlier on, where we had that intensity on the exit was proportional to the force we put in, and then an exponential decay, exponential minus mu A times L, mu A being the absorption coefficient. Then we can immediately see that these are the same, and that the absorption coefficient can also be interpreted as the probability of absorption per unit length. So that is just so if you now take a look at this, then mu A times dl is the probability of absorption in an interval that leads to a Beer's law for transmission in terms of intensity and the likelihood of transmission. Is then simply that exponential form. The probability of not transmission, that whole cuvette is then 1 minus that exponential factor. That is called a commutative distribution. See that a little bit earlier. So that is the probability of absorption. So in terms of transmission or absorption, it is the probability of absorption over the distance of L or less. So the probability that it is absorbed up until distance L. If L is infinite, then the probability of absorption is 1. And that makes sense. If you have an infinitely long medium, then at some point the photon will be absorbed. If it is 0, if L is 0, then the probability of absorption is also 1 minus, because it has not entered. So this commutative distribution function is then related to the probability density function by an interval. It's the summation of probabilities over given lengths, so that can be expressed as an integral. So if you differentiate that, then again, then you get the true form of the PDF. So the likelihood of absorption per unit length, the probability is P of L is mu A times exponential mu A times. You will check that that this is normalized if you integrate this over all possible path lengths, and they run from 0 to infinity, so not from minus infinity, but from 0 to infinity. Then this would yield unit. So the summary. List them quickly because they are in the slides, but this is for your for your reference. One question I do have for you is now, based on this and based on what we did before the break, can you calculate the expectation value or the mean value of the path length? So if we know, so the second bullet point is the PDF for the path length. So what is now the expected value? The expectation value for the recognize that it is very similar to the what we did just before the break. So. Go ahead, chat. So.
Should be 1 over mu8.
So, just realized I don't have it on the slide, so I'm just going to write it down. So that the expectation value of the path length is going to be 1 over 100. Okay, that was absorption. So now let's take a look at the other process, that's scattering. So let's say we have particles with a scattering efficiency Q of S. That means that you knew that the ratio of the scatter power over the incident power is Q. Another way of looking at it is that the fraction given by QS of photons that we encounter a particle is scattered. So if the scattering efficiency is 10%, that means that 10% of the power is scattered. The incident power is scattered, but you could also view it as only 10% of the photons that hit the particle are actually scattered, and the other 90% just continue as they went. Now suppose we have a suspension of particles. All these particles have a geometrical cross-section A and a density rho. So just defining that suspension. And let's carve a random path through that suspension. So the length of that path is L. And it is designed in such a way that it exactly captures particles as it goes in. In that case, the volume of that path, that snake, is V, is A, so the cross-section of the particles times L, the length of that snake. And the average number of particles in that snake would be rho times V, so the density times the volume fraction. The density times the volume is rho times A times A. This thought process was inspired by a game that my son likes to play on his phone. It's called, it's like a snake that eats a particle. Never mind. So what is then the so if all this is another joke that falls pretty flat. If this is really true, what is then the average number of scattering events in the stack? In this kind of snake? So the number of particles in the average number of particles in the snake is given by this amount. You can read the top line. So what would be then the average number of scattering events?
Q times whatever we have.
Yeah, Q times this. So the average number of scattering events would be Q times rho times A times L. Of course, Q times A was the cross section, so that would be, we can combine that. So here we have the rho times the scattering cross section, and rho times cross section is the coefficient. So we look this together. Scattering coefficient. So we have mu s times L, scattering coefficient. Would be the average number of scattering events. So what do you think would be the average path length between these scattering events? Yeah, same thing, just like with absorption. So it would be, so the mean path length between, so if you have a length L, you have on average n scattering events, and the mean distance would be L over n would be 1 over mu s. We just calculated for the absorption coefficient. Start with Beer's law. We calculated that the mean length before absorption was 1 over mu a. Now, a little bit different, from a little bit different perspective, we have the same result for the scattering. So what that basically tells us, it works just the same as it does for absorption. Just a summary. There's another way to prove. Show this. If these particles are randomly placed in the medium, then the distribution of the number of particles per unit volume follows a Poisson distribution. We talked about this class in the classroom. So it is truly random. We know it is not the case, but for now, let's assume it is. If it is truly random, then the number of particles per unit volume will follow a Poisson distribution. Then the number of scattering events, just by this scaling with QS, will also follow a Poisson distribution. So, including the factor Q here, but see what it will also follow a Poisson distribution. And then the probability of transmission, so basically not being scattered, can be found by filling in n is 0, so no scattering events. So if you substitute that into the Poisson distribution, so n is 0, then again the exponential Beer type law. So the formalism for absorption and scattering are completely equivalent. That is I can walk the argument back. So if that case, we could also define the probability density function for scattering free length. So the lengths that photons travel between scattering events would be this Beer type law. The mu s is now in front of it because it has to be normalized. The commutative distribution function, so the probability of scattering between 0 and L would be the green expression, just as for absorption. Yeah, that's good. So, okay. Let's now. This is a good moment for a short break again. 10 minutes again.
is het andere vak? Hoe is dat andere vak? Het is zo.
Ja. Nee, die volgende niet. Ik was gestopt.
Ja.
De eerste heb ik gevolgd en dat is dan wat ik dan voor probabilistic methods. Heb ik dan die is het is 1 keer per week.
Wat is dat dan?
Dat is
Oh ja, dat.
dit is naar best wel valt. Dus ik hoop dat het een beeld moet hebben. Vanaf morgen is ook zijn export options.
Ik wilde dat doen. Ik was te laat.
Over de aanbieding. Je kan altijd via data dus.
Ja, dat weet ik. Maar ik had al dat vak voor 2 keer per jaar gegeven. Dus
Ja.
ik ga dat vak dan later. Ik wilde eerst in periode 2 nog een ander schrijfvak doen. Maar dat had, ik dacht nee, dat is weer te veel van het goede. Dus daar heb ik Experientials bijgekozen. En dan ga ik nog 2 anderhalf punt van.
Ja, ik wilde eerst in de periode 3 gewoon
Ja.
6 in, maar dat komt niet goed uit. Dus dan moet ik wel die best van
Ja. Ja, en ik had daar geen zin in dat vak. Dus ik moest dan, want ik was ook eigenlijk best wel gebonden aan die losse vakjes. En gewoon een heel ander vak in de derde periode.
Ja,
Want wij hebben dus geen natuurkunde vakken in de derde periode.
oh ja, tuurlijk, ja. Leadership is de enige, zeg maar. Maar ik moest ook zo 6 essays.
Nou, dat is heel weinig. Als je kijkt naar wat je voor gaat jaar, dan is het heel weinig.
Want ik denk dat zeg maar 1,5 essay en ook meer workshop was. Dat is gewoon een
Dat is ook best wel leuk. Ik ga stel gewoon voor.
Echt heel jaar lang bij inkomsten kreeg ik die essay.
Ja, dat is echt. Er is gewoon niks van.
Gewoon net zo iemand best vertellen dat hij bij inkomsten dat hij
Ja.
Wat voor
ja, dat
Oh, je trekt
Hoe je plaatsen.
Die heeft daar echt zijn diploma niet op kunnen halen.
ja, dat is een beetje vervelend. Ja, die mag gewoon zelfs de master starten, maar die is maar even wachten. Eerst die bij inkomsten dat via zijn hebben. Ja.
Oh ja, je moest het gewoon echt iets van 15 punten. Het derde jaar of zo moet je 15 weken komt van 5 schrijven. Zo.
Hij vertelde dat hij naar de inkomsten gaat, waar hij dus daarom vertelt dat hij dus naar je bachelor kan doen en dan bezig is met zijn master. Dus ja.
Hij moet gewoon even inmogen inderdaad.
Ja.
En je moet je toen ook misschien aanmelden als je doet.
Ja, sommige waren best wel, zeg maar, ja, sommige spijken zijn best wel interessant, dat mensen echt gewoon met de SDF komen of zo.
Dat zou ook wel leuk zijn.
Ik ga dan ook studenten die daar kunnen zitten.
Ja, dat in mijn tweede jaar van meteen allemaal.
Ja, ik ook.
Ik denk dat ik niet heel erg veel later naar de eerste kant klaar ben. Dat extra aan mijn gevoel. Ik dacht zo snel mogelijk moet laten.
Ik moet klaar zijn inderdaad.
Maar het vak Explore heeft ook 4 workshops.
Het enige wat me van dat vak niet aansprak was dat je dat werk moest gaan netwerken. Toen dacht ik, ja, dat moet ook eigenlijk wel gewoon een keer gebeuren, zeg maar. Dan kan ik beter in een vak doen en een soort van begeleid worden.
Is dat een mastervak?
Ja, ja, 1,5 EC.
Oh,
Dat is echt zo weer zo'n 4 verleentjes.
in een
Vak en dan heb je dat
Ik moet CV meenemen. Ik had er eigenlijk eerst geen zin in. Ik wil niet met, over mijn CV hebben. Weet je, het is
Ja.
Oké, laat ik
Het is wel
aangaan.
nuttig.
Het is echt wel een en je weet na je master gewoon precies. Als het goed is, dan is dat als doel. Dat je precies weet waar het naartoe gaat. Niet zeg maar alleen maar. Het er ook nog meer.
Ja, maar ik heb het idee dat het heel veel
Je had
Ja,
de
ook
meeste
wel
snel
lijken
uit.
samen met ons.
Ik verwacht toch iets meer dan wat je zelf
Wat was jouw plan om in te vullen met die professionele vaardigheden?
Ik ga entrepreneurship voor
Dus
fysicist.
dan ben je meteen klaar.
6 punten.
Ja, wel,
Ja,
4 weken lang. Ja, maar best wel leuk. Ding, misschien
aan
een
de
beetje
noord
bedrijf.
om te lezen.
maar
Misschien voor community.
Best wel leuk.
You can pick like
Maar andere
the
optie.
door.
Ja,
Just
dus
like
dus ik bedoel,
under.
ja,
This
ook,
class.
ja, goed,
Yeah,
ja,
the only way
vier
to
keer
work
allemaal
is
wc.
with the kind.
Dus dat is 4 keer 4 werkcolleges, verschillende dingetjes. Dus het voelt waarschijnlijk wordt dat explorer options.
Nou, ik denk, ik ga 2 keer anderhalf en dan in de 6e periode heb ik 1 voor business.
Ja,
De 6e periode ga ik dat en
Oh,
dan
oké.
als ik bij
Ah.
dus maar dat wordt in Brouwer van ze zei ja, dat is wel dus dan ga ik dat
Maar je hebt nu het scientific writing.
ja, dat is vandaag, dat loopt dat wordt dus
Ja,
klaar.
donderdag afmaken.
Ja.
Nee, ik heb mijn opdracht al af. Ik
Ja.
ga alleen maar feedback ontvangen en dan feedback verwerken.
Ik heb er echt wel idee dat het wel wordt.
Het is nuttig en leuk. Het is ook echt leuk.
Oké.
Gewoon een snelle opdracht is.
Ik heb al dingen echt geleerd van oké, echt veel eerder moeten weten, maar ik ben dus bijvoorbeeld.
Ik denk dat het ietsje meer werk is dan allemaal facing. Normaal zo. Allemaal facing. Ietsjes minder. En dan merk ik toch van, het is een op zichzelf staand vakje, dus dan gaat het wel gaan. Precies. Denk ik.
Wat gaan we nog doen?
Oh, ik heb dat.
Ja, en ik voel bias is toen ja, dat is net een computational scientist.
Ja.
Dat is wel grappig.
So the goal of this very long introduction was to see if we can get a simpler model for the light detection probability. Let's say for this geometry, for this single finite geometry. The key assumption is here that the light is backscattered only once, so you can have multiple number of scatterings in the forward direction, but it is only backscattered once. And the validation or the rationale between that assumption is that the G value for the tissue is generally high. So that means, and like you said, the G can be interpreted as the fraction of light that retains its original direction. So if that is high, then that means that a lot of light is just basically scattered in the direction that it came from. So the model would then be to have to have a lot of light just being scattered in the original direction, and one distinct backscatter event, so where it reverses direction, and then on the way back to the detector, to the fiber, it will again retain its direction. Other ways of formulating that is that the possibilities of being backscattered 3 times. So if you would want to have, so if light is coming in here, and you want to have it detected here, it can either be 1 time backscattered, or so 2 times backscattered would put it back to the original detection. So you would at least have the next possible option would be 3 times backscattered. So 1 time back, then back again, and then back to the fiber. Or 5 times backscattering, etc. So you would need to have an uneven number of backscattering events to maintain reflection. Because of that high anisotropy that is usually there, then these likelihoods are increasingly less. So 3 times backscattering is already very likely, and 5 times even. So in that model, what that means is that that propagation takes place along, let's say, an infinitely long line placed along the fiber direction. So it's a true simplification of the model, but that is what we're going to work with. And at first, we're also going to assume that there is no absorption. We can factor that in. This will, you can understand that this will only model part of the signal. It's not full signal, but the idea is to see how far we can get from this. And the full model is more complex, but also is built on this these assumptions. And so again, the same slide all over again. These are the probabilities that we need to find, that we need to calculate. So that the scatter-free propagation 2.1 over a length L1. Then the probability of scattering at 1.1. Then the change of direction of the photon from wherever it was to 2.2. Then the propagation to scatter-free propagation to 0.2 over length L2, etc. So I'm going to give you an expression here. And hopefully these terms are by now somewhat familiar. So here we have what we discussed before the break. It was the same like absorption. So exponential minus μs times L1 is the probability of traveling, the photon traveling length L1 without, in this case, any scattering. So that is basically in the graph is the probability of traveling from the boundary there to the point L. Then the probability of scattering at a certain position was, of course, the likelihood of scattering was given by μs. Then μs times dx is then the probability of scattering exactly in that small interval. Then the probability of changing direction, so let's say from direction S1 to S2, it's given by the phase function. Then the next step is, if we follow this trajectory, is propagation to over a length L2 without being scattered again by this exponential. Then the probability of scattering at S2 propagation is again μs times dx. We assume that scattering probability is the same in each location. So that would be the same. Then the change of direction, again the phase function, etc., etc. So doable. Okay. So then now let's look at zoom in on such a trajectory. So propagation on a line where there is one scattering event. So on top is the dotted line on top is the propagation that the photon will take when there was no scattering event. So probability of traveling a length L without scattering would be exponential minus μs times L. But now the question is, what is the probability of traveling a length L with one scattering event? Somehow I always mix up likelihood and probabilities, so that's against me, please. So if you look at the cartoon there, so with a distinct scattering happening at one place, then it means that we have interaction-free propagation over the length L1, then an interaction at L2, at L, so US. Oh, it's because of the axis not there. US, and then a propagation again over length L2. This would be no, first. These probabilities are all independent. So we are allowed to just switch out the order of multiplication. We can group the two exponential terms together, and the L1 plus L2 is simply L, the total length L. So we can have an exponential term here times UF. But scattering event at 1 here can occur anywhere along that path. So now it is drawn here, but it could also occur early or it could occur late. So if we want to have the likelihood or the probability of let's say transmission with one scattering event, we have to add all these possible options. We have to add all these possible positions. So according to the recipe, we have to add all these options. So we have to add all the options where this point 1 is located here or there or there. Of course, if you make that continuous, it becomes an integration. So we can write it like this. So the total probability of transmission along that line with one scattering event is μs times, so just this factor. But then accounting for the fact that one position can take place anywhere between 0 and L. So it can take place immediately at 0, it can take place at L at the end. It could also take place at so we have to add all these probabilities, integrate all these probabilities. So and that would add a factor L. So this would yield a factor L. The good thing that you can verify now is that this is μs. What's the answer of μs? Yeah, per meter. This is meters. So this is a truly dimensionless number. So this is really a probability. And another thing, so we vary the position of the first of the scattering event 1. So I call that Z1. That is of course also the same as a path length technique. All right, now how about 2 scattering events? So same length. What is the probability of transmission along this line when we have 2 scattering events? So for this particular event, which is given here, we would have a probability of traveling to L1, so that is without any interactions, that would be exponential, this exponential term. Then the probability of scattering at 1, then the probability of scattering at of propagation to L2, probability of interaction at L2, and then the final probability of propagation to the So what do you think happens here? Again, these are all independent events.
It's the same as before multiplied which.
So these exponential terms can be grouped together. So L1 plus L2 plus L3 in this case is just L. And then the μs's are the same. So you would get something. You would get this. So the path probability would be exponential μs times the length, and then the prefix, then a factor before that of μs squared. But that would be for this particular path. We have to add all the possible ways that this path can occur. Now the second, it's easier to look backward. So let's say that the second scattering event could occur anywhere between 0 and L. The first scattering event can only occur between 0 and the second scattering event. So that means that if we have to add these probabilities, that means that that the second scattering event, so that is the outer integral here. So we factor out all these prefactors. They do not depend on the coordinate. The outer integral runs from 0 to L. Second scattering event, and the inner integral, the first scattering event, runs from 0 to the position of the second scattering. So then, if we first do the inner integral, I'm sorry, then that would be the result would be Z2. Then we can go. Then we do the outer integral Z2, Z2 over 0 to L, and that will be the front. Okay. And again, so these integrals have with increments dz1 and dz2, but these are just increments on the path length scale. So dz1 is equal to dz2 is equal to bl step size. Okay, now see how this scales up to n scattering events. Can you make a prediction? Okay, three events. So the third event, again, reasoning backwards, the third event can be anywhere between 0 and L. The second event can only be between 0 and the third event, and the first event can only be between 0 and the second event. So the same thing. So we can write out this whole sequence of probabilities. So exponential. Negative exponential for the travel between over L1, and then the probability of scattering at 1, then the exponential again for travel over L2, etc. In the end, we can group these exponentials together, so that will just yield again a factor exponential US times L. And now, because we have 3 scattering events, we have 3 times US. So of course, that is also, we can also put that in integral form. So the prefactor is here, and then here is the integral for the typos. So the third integration would run with the third event would run from 0 to L, and the now, but I will correct that later. I hope you get it. So you can work these intervals out, and then in the end, the result is this. So for 2 events, we had the US times L to the second power. Here we have the US times L to the third power, so that scales with the most scattering events. We always have this exponential decay that is just related to the total length, and the factor that comes from the integration. If we repeat this for any number of n scattering events, then the generalized probability is given you some US to the power of US times L to the power of n divided by n faculty. That is due to the repeated integration, and then the exponential term that is just related to the length of the particles. Yeah, and all these increments in the integration. So if you would plot that, so so let's take a given path length in a given scattering order, so the number of scattering events. Then for n is 0, so that would be just the exponential decay with a blue line. For n is 1, it would be the red line, etc., etc., etc. So what you see here now, for example, is that if you have a let's say you have way of only measuring photons that have traveled half a millimeter, so that would be this case, then your signal would be dominated by photons that have been not scattered, or maybe scattered once. All the other photons are not really contributing. If you go at longer wavelengths, so let's say 5 millimeters, then your signal will be dominated by photons that have been scattered for more times. So that is one way of looking at the result. So in case of this signal fiber reflectance model, where we assumed that photons would scatter along a line and then or back scattered once and then or scattered back. We would have to include not only the probability that the photon is scattered, but also a probability that the photon is scattered exactly in the forward direction. So that is going to be related to the phase function, to G. To keep it a little bit flexible, let's just assign a forward scatter probability factor PF at any effect. That would just mean that in the whole analysis that you would include at each scattering step, you would include this factor PF. So you have a probability that the photon travels over a given length, and then there is a probability that it scatters, and then there is a probability that it is exactly scattered in the forward direction, PF, and then there is a probability that it travels again. So that would be that could be simply included, and that means that it just appears in this. So let's keep saying this. The backscatter effect, that is a slightly more complicated, because it can also take place, of course, anywhere between 0 and infinity. So we assume that the photons travel along that line, and the backscatter event can basically move across this line. Statistically speaking, it does not really matter where it takes place. It is the first, so let's say we have n forward scattering events. That is the expression that we just derived. So let's say 5 or so. It does not really matter if these 5, if we have 1 forward scattering event, then the back scattering event, and then 4 forward scattering events again to make it 5 complete, or we have 2 and then 3, or we have first 5. And then 1. That does not really matter. So basically that we don't need to take that into account in the integration. So what we can do is we can just calculate the probability. So with 1 backscattering event and any n forward scattering events as the integral of the probability of having n forward scattering events wherever they take place, and then weighted by or integrated by the probability of 1 backscattering event. So that will be again US for the 1 backscattering event. PB would be the probability of being scattered in the backward direction. And then we have to have this integration variable. Now this is where the emphasis on the integration variable comes along, because up until now we had integrations along the length, so dl and dz would be the same. But now, because the photon is scattered here and is basically turning back, L is a unit of path length and Z is a unit of position. So that gives a little bit of a discrepancy. So for propagation along a line, so let's say that the photon is scattered at position ZB, then the length of the path would be 2 times ZB. Any propagation is a straight line, so if the position of the backscattering event is ZB, so then it's the length ZB to here and length ZB back to the z-vector. So in that case, L would be 2 times ZB, and then DL or DZB would be half times DL. That is a little bit contradictory, and it does not work. So I'm not going to into too much detail for this, but if we do it like this, so if we would substitute DZB for then it does not work. We have to really work with the DL steps. So the proper. I know this is a little bit sloppy. The proper form of the integral is to use DL. So this integral is then something we can perform. So PB is just a constant that can be taken out of the integral. US is also just a constant. It can also be taken out of the integral. And the only thing that we are left with is then perform this integration. So now let's say we want to know all the sum over all the possible number of forward scattering events. So only one backscatter event with any end. So that would mean that we need to sum, according to the recipe, we need to sum from n0 to infinity of P of n. P of n that we just had the expression for, so we can fill that in. And it would the result would be this. So it's an integral and a sum with backward scattering probability, forward scattering probability, and scattering coefficient. There's 2 ways to go about it. We can first do the summation, then do the integration, or we can do first integration, then summation. Which one do you prefer? Bluffing on my part because of course I don't. Okay, so this is really not something that you have to learn by heart. It's just I want to show this. So let's do the summation first and then the integration. So this was the expression. So we had so I'm taking the backscatter probability out of the integral in the US. It's a constant out of the integral as well. I'm not sure if you recognize it, but this is a standard sum. So see it in the box there. So we can refactor that sum into an exponential form like this. So that would become exponential of mu s times pf times l, and then the other exponential term. So we can then group these 2 exponential terms together. A little bit of manipulation for the minus sign there. And then, of course, this is just a standard exponential interval that we can solve. We can substitute here for L prime is L times 1 minus PF. Adjust the integration boundaries. That is not really necessary because they run from 0 to infinity, so they keep running from 0 to infinity. That expression there, well, you recognize here the PDF of path length itself. That was normalized, so this integral is going to be evaluated to 1, to unity. So the final result is then the probability of signal probability of all possible number of interactions in the forward direction and 1 interaction in the backward direction related to the signal probability is given by this expression. So we have it scales linearly with the probability of backscattering. That makes sense. If you have the probability of backscattering is stronger, you will have more signal, and it scales inversely with 1 minus forward scattering probability. And that kind of also makes sense because if a lot of light is scattered away, then they would not detect it. Okay, just for the fun of it, the other way around. So if we do the integration first and then the summation, that is also it is insightful. That is why I want to show it. So we can rearrange it. We can change the order. So change the order of the summation and the integration here. That's what you see here. This is also again if you first substitute. So now substitute L prime is mu S times L. And to get the integral there, and this is also a standard integral. So combining that, we end up with this solution. First with this solution. This is nice because it shows you that this probability scales. Of course, it scales with the backward probability. That is still the case. It also immediately reveals how it scales with the probabilities of the number of forward scattering events. So that of course is also again also a standard sum. So that in, and then luckily the same result is obtained. That should be the case, of course, because it should not matter. PB over 1. Yeah, that was the point that I wanted to make about this intermediate equation. So for each higher order of n, so n is the number of forward scattering events, the contribution to the signal decreases with a factor pf. For low pfs, so for moderate forward scattering, so real terms with for low g values of the phase function, and the lower orders are the only ones that really contribute to that signal. Okay, so now we had PF and PB in there as factors that described the probability of in the forward direction, the probability in the backward direction. That was a nice accomplishment, but we would like to tie that to some physical measure of the system. So one of the thoughts was, and this was just how we tried to solve that, is to tie it to the numerical aperture of the fiber. You know what it is? So the NA is the it says that it's the sign of the theta NA. Theta NA is the acceptance angle of the fiber, or of so whatever. It is how under what angles can you still receive it. The idea was that just intuitively that only photons that scatter within the NA, so within these angles and these small angles, that they can still be detected. If the scattering angle is larger than that, then we just assume that it is mixed. So you can make that calculation. So this is a plot again of a me phase function of a particle. Let's see, what is it? It is a particle of 150 nanometers. So it's I think that should be micrometer. Small, with a wavelength of red laser wavelength of 632 nanometers. Most of the light is scattered in the forward direction. As you can see on this polar plot here, a little bit of light is scattered in the backward direction. So if you would integrate this phase function over an NA of a 0.22, so that would correspond to an angle of something similar. Then the PF, so the integration of the phase function over that forward angle would be 6%. The backscatter probability would be 0.5 per mu. So again, so the over theta and A would be the angle that corresponds to the numerical amplitude of the system. The forward direction that would correspond to an integration over 0, so the forward direction to theta and A. That's the integration boundary here. 2 pi is because of the rotational symmetry, of course. In the backward direction, P. The angle P would be the complete backscatter direction, and P minus and A would be the acceptance angle. Okay. So if we combine all these things, then this no, that's a storyline of the next slide. So if you look at the intermediate results, so we have this integral that's still was to be worked out to get this final expression. You can see that the probability of I'm not sure what my message here was. Sorry. Oh yeah, of course. So if you form this into an into this integral form that runs over the L, if it is properly normalized, it means that you kind of have a probability density function for path length L. So you can factor or refactor that equation that was one of the intermediate steps into this form. So probability density function of L. Combining these terms would look like this. And if you properly normalize it, it would be a true probability density function. So a normalization of this would mean integration and then equating it to 1. You would get the constant out of it. Result in this expression. So this would be the probability density function of path length L, for all the photons that have traveled any number of scattering events, but with only one backscatter event. So that would be the situation. So if you have this probability density, you put the calculator, the average, the expected value of the path length. So that would mean multiplying this function with L, integrating it over 0 to infinity, and the result of that is given here. So the average path length is 1 over US times that's 1 minus P. If that is the average path length, that is back and forth to the fiber, you could say, okay, then the average depth that the photons get, so the average depth that you can measure with, is half of that, because they have to go back and forth. So the average probing depth should be given by this expression. So dependent on the scattering coefficient, but also dependent on the forward scattering probability. The second point is that this expression does not include yet the absorption coefficient. Well, it says scattering coefficient here. I mean absorption coefficient. That was really a little bit. Okay. So that means that if we only consider scattering, then scattering is only redirection. So there is no loss mechanism. If the medium is infinite or semi-infinite, then the only way that photons can be terminated, let's say, is that they escape. They must escape. So formally, formally, what you see here on formally the right hand side of this equation should be 1, because if the only mechanism for photons to escape is to be re-emitted, to be reflected, then each of them should be detected. This, of course, is not 1 because P and PB and PF have finite values. So it is important to realize that this does not describe the total reflection. This just describes the fraction of the photons that have had only one extra movement. If it is either scattered or absorbed, we can express the probability of scattering as a factor alpha, which is called the scattering albedo, which is the ratio of the scattering coefficient and the sum of the scattering coefficient and the absorption coefficient. So the probability of scattering per unit length was μs, the probability of absorption per unit length was μa. So the probability of anything, either of these two happening per unit length is μs plus μa. So then, and these are the only two mechanisms. So then the probability that it actually is scattering is the μs. So we can include that as well into the just like we included PDF. So now at a certain location there is an interaction. There is a probability that it's a scattering event or an absorption event that is now alpha, and there's a probability that it is an event before interaction, which was counted. Like, so you can include that directly into the equation. So then the simple equation remains actually quite simple. Only now there is this alpha to include. That does mean that the average probing depth is a little bit changed because now it also includes alpha here in terms of the absorption and scattering coefficients. So also this kind of makes sense. So if the absorption coefficient is very high, then the probing depth gets less. So the absorption is high, you measure less deep. All right. Yeah. So the summary, basically the summary of what I wanted to tell you is that we have this very simple technique, but there was a very complicated model, and the thing we decided to do, or we thought we could do, is to just start from scratch. To start from instead of doing multicolor simulations, try to use these probabilities that we knew for each of the events and try to build up a model from that. To see if we can model this distribution. The result you have seen in the last slide. So that includes forward scattering probability, backward scattering probability, and also absorption. The simplifications are, of course, quite restrictive. So the assumption that the photon is scattered only once is restrictive. The assumption that propagation takes place along a 1D line is also very restrictive. So it is not a complete one. It is. It did turn out to be useful. So yeah, we managed to publish a few papers about it. It's not finished yet. So if you like this kind of thing, then please let me know. And I have a lot of projects that can help bring this through. But the good that's really the last thing that I want to say about it. The good thing about this technique is that experimentally it is so simple that we can use it almost immediately in the clinic. So many of these techniques that we investigate are complicated, and mathematically they are fine. They're physically they are exciting, but usually it's bulk setups, large equipments, not something that you can easily apply to a patient. And with this, even though we have to prove a lot of things, at least this is something that is usable in the O1. So that from my perspective, that makes it exciting. That is then the very last thing I want to say to you today. Thank you. I don't think that, yeah, that's blank.
Die fibers can also
Yeah.
really fibers like inside the study plug, so with some needles.
Yeah, so that's a really good thing about it. So you can put it in a so the fibers are maximum 200 microns thick, so that's kind of thick. So but you can put it in a needle, so you can basically use that to get close to a tumor, for example. You could put it in an endoscope, that's for sure. So like everything you can reach with an endoscope, so that could be the esophagus, could be the bladder or the stomach. Yeah, so you can get there. You don't need large. It is just the interfacing part is just there. One of the things that we're trying to do now is so for biopsies. So the current way of doing diagnostics is basically to take out tissue, take a biopsy, look at it on the microscope, and see if it's bad or not. It's the first, so have a needle in place which would eventually take the biopsy. First, put our fiber in, do a measurement. Then they will take a biopsy, and then we can compare. That's something that you would not be able to do so if you think of any new technology which would require an independent microscope or independent, you would not get permission to do that because it would be too dangerous. But in this case, it is okay. The needle is already there. You can use the same channel, just do a quick measurement, get the data, and then the normal procedure. So that makes it much more powerful.
Yeah.